You know, there's a technology out there that's so incredibly precise. It's like performing surgery on an individual atom. It's a process that unlocks a truly staggering amount of power, but it also carries this immense weight of responsibility. We're talking, of course, about uranium enrichment.
And it really all starts with this question. How do you take a rock, something you just pull out of the ground, and turn it into a fuel source so powerful it can light up millions and millions of homes? And why can that very same technology be a source of clean energy and, at the same time, an object of serious global tension? The answer lies in a fascinating process of atomic separation.
All right, let's get right into it. The first thing you have to understand is just the massive scale of the challenge here. When uranium comes out of the ground, it's nowhere near ready to be used. It's more like a giant atomic haystack, and we're on the hunt for a very, very tiny needle.
So here's the deal. Natural uranium is mostly made up of two different types, or what we call isotopes. More than 99% of it is this stuff called uranium-238, which is pretty stable. But the real prize, the needle we're looking for, is uranium-235, and it makes up less than 1%. U-235 is special because it's fissile. It's the one that can actually sustain a nuclear chain reaction. Now here's the problem. Chemically, these two isotopes are identical. You can't just use a filter. You have to rely on the one tiny difference between them. U-235 is just a tiny, tiny bit lighter. And that small difference, well, it changes everything.
And that right there is what enrichment is all about. It's just the process of boosting the concentration of that super useful U-235. You're taking it from that tiny 0.7% all the way up to a level where it can actually power a reactor. But how on earth do you separate atoms based on a weight difference that's almost nothing? Well, that's where some incredible engineering comes in.
So how is it actually done? Let's get into the most common method used today, which is basically the world's fastest and most precise spin cycle.
The absolute champion of modern enrichment is the gas centrifuge. Now, this isn't brand new tech. Its origins go all the way back to the Manhattan Project, but it has been perfected over decades into this incredibly efficient, unbelievably precise machine.
So how does this thing work? Well, first off, you can't exactly spin a solid rock. So the uranium gets converted into a gas called uranium hexafluoride, or UF6. This gas is then pumped into these tall, spinning cylinders called rotors. And when I say spinning, I mean really spinning. As they rotate at these just mind-boggling speeds, centrifugal force takes over. It's just like how laundry gets stuck to the wall of a washing machine on the spin cycle. The heavier gas molecules with U-238 get flung to the outside wall, while the slightly lighter U-235 molecules, they tend to hang out a little closer to the center.
And the speed we're talking about here is it's staggering. We are talking about tens of thousands of revolutions per minute. The outer wall of that rotor is moving faster than 500 meters per second. That's literally faster than the speed of sound. This creates a gravitational force hundreds of thousands of times stronger than Earth's, powerful enough to sort atoms by a weight difference of just 3 neutrons.
But of course, there's a catch. One spin is not nearly enough. The separation you get in a single centrifuge is microscopic. To get from that 0.7% U-235 up to the 3 to 5% you need for a reactor, you have to amplify that effect thousands and thousands of times over.
And this really gets to the heart of why this is so complex. The big secret to enrichment is just repetition, repetition, repetition. You take the slightly enriched gas from one centrifuge and you feed it right into the next one, and then the next one, and then the next one after that.
Okay, so to process the sheer amount of gas you need, hundreds of these centrifuges are first linked up side by side in what we call parallel. This whole group is called a stage. Every single centrifuge in that stage is doing the exact same job, just processing a little piece of the total flow. And this is the next critical part. These stages are then connected one after another in a series to create what's called a cascade. So the slightly more enriched gas from the center of stage 1 gets piped over to become the input for stage 2, and the slightly less enriched gas from the outer wall, it gets sent back down to a lower stage to be run through again. This process is repeated through thousands upon thousands of centrifuges, and with each step, the uranium gets a tiny bit richer in U-235 until finally you hit your target.
So we've gone from sorting single atoms to this massive, sprawling, industrial-scale cascade. All that complexity, all that incredible precision, what does it all get us? Well, this is where we really see both the immense power and the inherent peril of this technology.
See, the level of enrichment completely determines what it's used for.
Low-enriched uranium, or LEU, is usually enriched to somewhere between 3 and 5%. That's the standard fuel for pretty much all of the world's commercial nuclear power plants. But if you just keep that cascade running, pushing the concentration way up past 20%, you get what's called highly enriched uranium, or HEU. And this is the really crucial part. The exact same technology that creates clean energy can also create the material for a nuclear weapon. This dual-use nature is precisely why enrichment is one of the most sensitive and closely guarded technologies on the entire planet.
So what's stopping anyone from just building one of these plants in their backyard? Well, it's an absolute engineering Everest. I mean, think about it. The rotors have to be built for materials that are stronger and lighter than steel, like carbon fiber composites, just so they don't tear themselves to pieces. They have to be balanced so perfectly that the tiniest vibration would mean catastrophic failure. The whole system runs in a near-perfect vacuum. It has to handle a gas that corrodes almost anything it touches, and it has to do all of this nonstop for more than a decade.
It's wild when you take a step back and think about it. An entire global industry, the electricity for hundreds of millions of people, is all built on exploiting a weight difference of just 3 subatomic particles. It's a breathtaking testament to human ingenuity, a combination of physics, engineering, and precision on a scale that's just massive.
And that kind of brings us to our final thought. This incredibly complex, high-stakes technology gives us an enormous amount of carbon-free energy, but it also presents these profound challenges of safety and security. So the question we want to leave you with is this. As we keep searching for ways to power our world, what role should this incredible technology really play?